welcome back to the series of lectures on electrical circuit analysis. So today I would like to discuss transients and initial conditions part. In the previous lecture series, I had discussed about the source and source transformations and source shifting concepts. So what are transients and why initial conditions are necessary for us to analyze any circuit given with excitation DC or AC excitation. Okay? So let us first look into what exactly the transients are, and why it is important for us to consider the transients in our analysis. So if I have to give an example, assuming that many of us have used the analog meters to measure voltage, current or any other parameter, where by giving or by connecting the meters into the circuit or in the system, when the excitation is given or when the switch is closed, we see a pointer will be deflecting from its initial position to some final value. Okay? If I consider a voltmeter, for example, I consider a voltmeter, an analog voltmeter. Okay, specifically I am telling about analog. So this is the positive terminal, negative terminal of the voltmeter, and if I connect this to a circuit or to a source which is at say 10 volts, and the range of this voltmeter is say for example 0 to 20 volts. Now purposely I have taken the voltmeter of higher range. Okay. Now if I see the marking of this voltmeter, there are continuous markings. At the mid I will see 10 volts. This will be 0. This will show 10. This will show 20. Okay. Now when I, for example, suppose I use a switch. I use a switch in series with the battery. Now the moment I close the switch, at any instant when I close the switch, then the pointer of this meter will deflect to show the amount of voltage applied if that is in the range of its scale. Now the moment I close this switch, at some time, I assume always the time at which I close the switch is 0 instant, the initial instant. Okay. So when I close the switch, T is equals to 0, this voltmeter will show the applied voltage by deflecting this pointer, okay, towards 10 volts. This is what I expect. The moment I apply 10 volts, here, I expect this pointer to start from 0 and stop at 10 volts exactly. But if you have keenly observed, or hereafter when you measure any parameter using analog voltmeters, this is true even with the digital, the pointer will not rest on exact 10 volt marking instantaneously. If I have to zoom in and see, or if I have to take the pointer deflection, suppose this is the 10 volt marking, okay, on the voltmeter, and if this is the pointer where it has to rest, okay, suppose this is the pointer. Now when it deflects from its 0 position or initial position to the final position, it will not rest here instantaneously, but rather you can observe the pointer slightly. First it will deflect after 10 volts, after it will deflect below 10 volts, again it will go above 10 volts, again it will come below 10 volts. After some such oscillations, okay, finally the pointer will settle down to the exact final voltage what I have applied to the circuit. So here I have applied 10 volt to the circuit, so the pointer will show now 10 volts reading. Now the question is why this happens? Why this happens? Okay, this will not happen continuously. This will happen only when I close the switch, and this will happen for a very short period. If the meter is well designed, well damped, if the oscillations, if the damping factor of the meter is very good, then these oscillations will not be observed to a large extent. Okay, with one or two oscillations it will settle down. If the meter is not well damped, then there may be more oscillations going on until it reaches the final position. Now, suppose if I plot this oscillation of the voltmeter with respect to time. Okay, now if I plot this oscillation of the voltmeter with respect to time, I take x-axis as time and y-axis as voltage. Now it is a steady voltage applied to the circuit. It is a steady voltage applied to the circuit. This is my final value expected. Okay, that I expect this voltmeter pointer should show me the 10 volt marking on the voltmeter. Now I will take the 10 volt here. This is my 10 volt marking. Now this 10 volt marking I expect. Now instantaneously what I do at t equals to 0 is the instant when I close the switch. I expect if I have to take, I will show it by some other color. So now my expectation is that the moment I close the switch at t equals to 0, I expect the response of the voltmeter should be like this. That instantaneously the pointer should deflect to 10 volts and dot at t equals to 0, it should stop at 10 volt marking. But practically this won't happen, because when the torque is developed in the pointer, when the deflection torque is developed in the pointer, because of the momentum of the pointer gained to deflect from 0 position to the final value, the pointer may not stop exactly at 10 volt marking. For an instant it may show the voltage above 10 volts, after it may come below 10 volts, again it may show some above 10 volts, some below 10 volts, and after some amount of time, and though that time is very short, after some amount of time this pointer will show exactly 10 volts. Now if I have to mark that, if I have to plot the values shown by this pointer during its oscillations around or about the 10 volt value, then it will rise. I will choose some other color as it is not so clear. I think yellow will be better. It will rise from 0. Instead of stopping at 10 volts, it will show some value about 10 volts. It will come down. Again it will go up, come down, go up, come down. At one final point, it will settle down. Okay. Now observe, the final 10 volt reading is available for me after say some value Ts. I call this Ts as settling time. The pointer has settled down to the final value of the applied battery voltage. Now if you observe, now hereafter, say for all the values of t, okay, all the values of t, t tending to infinity, the value will remain 10 volts. Suppose if there are no errors, if there is no internal drop in the meter, the value will be shown exactly 10 volts. Okay. Now if you observe this graph, if this plot, the voltage versus time plot, this plot has got two parts. Okay. It has got two parts. In one part, there are oscillations present. In other part, the value is steady. In one part, the oscillations are present. From 0 to settling time Ts, there are some oscillations, though they are damped oscillations. And on the other part, after Ts, T equal to Ts, there is a steady value. Now, if I have to analyze the operation of the voltmeter, then I can say that the voltmeter is a instrument where it will give the response in the form of a meter deflection or the pointer deflection corresponding to the value applied to its terminals. Now, if I have to only analyze this particular part, then I can say that this voltmeter has got two responses in its final output. One response will contain the oscillations, other response will contain the steady value. So the part that contains oscillations is known as transient response. It is transient response. The part where the output is remaining steady is called steady state response. I will write it here. Okay. Now if I have to collect back the things what we have studied in the previous sections of your curriculum, where we applied node voltage analysis, mesh current analysis, voltage transformation, so source transformation or source shifting, nowhere in our analysis so far have come across a quantity called time. We did not analyze the circuit with respect to time. So all the analysis what we did so far in the previous study is the steady state analysis of the circuit. We have assumed that whatever the source value we have given to the circuit or we have mentioned in the circuit and the circuit parameters will not change for the entire term or the entire time of operation. We have assumed already the switch is closed, this switch is closed at some t equal to 0, and I am analyzing the circuit, and I was analyzing the circuit for a value of t which is much greater than Ts. It means that all the analysis what we did so far in our study, we did under steady state conditions where the applied voltage to the circuit, remained same and it did not change. So this transient part has never come into our study so far. But that doesn't mean that always the circuits operate under steady state. Now if I consider the large voltage applications, like say for example in our domestic applications, I turn on the switch. If I have to turn on the lamp or the fan or any appliances in my home, I turn on the switch and the appliance will start operating. There, steady state analysis and transient analysis we generally don't consider because the transient time is so small that it may not affect the applications or appliances which are working at a larger scale. But say for example, if I have to operate a control system circuit, okay, today when we observe, everywhere we have automation. Everywhere we have automation. Even to open and close the door, there is a proximity sensor used to control the temperature of this room. In air condition, there is a temperature sensor. Okay, so in control system applications, transients play a very important role because control system applications demand the use of sensors, and the sensors are totally depending upon their sensitivity. Okay, how best sensitive they are to the changes that we apply in the form of a voltage, current, or any other physical quantity. Now, in such applications, if the transients exist, then these transients may lead to some undesirable results, okay, which may cause a operational hazard for the system. So, for example, if I take the room temperature sensor itself. If I take a room temperature sensor itself. Now this is a air conditioned room. The temperature sensor is continuously sensing the ambience temperature, and it is keeping the value of or the AC temperature, say, for at 24 degrees centigrade. Now, if it is an automatic closed loop controller, if the temperature rises, if the temperature of the room rises, okay, then the AC has to again cool down the room temperature. So, for example, currently I am the single person in this room. So, the ambient temperature is at some around 24 degrees centigrade. Suppose all of a sudden some 20 to 30 members get in. Automatically the room temperature increases. Then whatever the current temperature setting in the AC is there, that may not be sufficient to comfort this ambience. So now temperature will sense the room temperature and it will give signal to other control circuit that the temperature has to be lowered down, so that, or the coolant has to be enhanced, so that the room temperature is again kept back to 24 degrees centigrade. Now, if those 20 people are existing or they are residing in this room for a long time, then this is fine. Suppose every now and then a person is getting in and getting out. A few people are getting in and getting out. Suppose 5 people come to talk to me or to get some signature or whatever the work is, they will leave immediately after few seconds. Then what about the temperature operation, the sensor? Will it have to oscillate in its operations? Okay. So these are certain transients that will exist. So why in control system application the transients are important is the intelligent system should be well capable of understanding the input whatever it is getting is a transient or it is a steady state input. Even it applies to the response. Okay. Another electrical example if I have to give. Okay. The best electrical example if I have to give. We know that we are using circuit breakers everywhere. Okay. The circuit breakers are used to eliminate the overcurrent conditions. If there is a overcurrent condition, the circuit breaker will trip, MCB will trip, and it will protect the source as well as the load. But there are certain loads. So for example, if I am using a motor, the motor, though it is rated to operate at 10 amperes, when I start the motor, it may take as high as 50 amperes of current. Because starting current of the motor is always very high. Even if I consider the LCD tubes, these are all the capacitive loads, and when I turn on the capacitive load, it takes large current. So that large current demand initially doesn't mean that large current is existing throughout the operational time. That may exist a very short span of time. So that short span of time where the final value of the quantity is not settled down is called transient response, or is called transient period or transient time. Now what is my motive of studying this particular topic here is, when the transients exist in the circuit or in the system, what is the system response with respect to time? We know how to get voltage, current, power, everything for a circuit under steady state conditions, which we already have studied in the previous topics. In node mesh analysis, using theorems, using circuit reduction techniques. But what happens when I immediately close the switch or open the switch? Because there are certain circuit elements whose response are depending on time. So when I consider the electrical circuit, so electrical circuits are always characterized with, or they are characterized by, or they are realized by three components: resistance, inductance, and capacitance. So the response of these circuit elements depend upon the time. Okay, what we study initially in this part is how these elements are responsive to the applied voltage or applied current when the switch is closed. When I close the switch at t equal to 0, say for example, if I take a simple inductive circuit, and I connect it to, say, a DC source, a steady state source. Let it be V with respect to time, say t, V of t. This is L, and this is switch. Okay, switch S. Now when switch S is open, it is evident that no current flows in the circuit. So there is nothing happening here. The moment I close the switch at, say, t is equals to 0, always I consider the instant when I close the switch is the 0 instant. Okay, because it is very easy for me to start from the 0, t equal to 0 time. Okay. So when I close the switch initially at t equals to 0, suddenly the current rises in the circuit. Okay. And initially when the current rises in the circuit, what is the response of this inductance with respect to time to that current or applied voltage that we have to study. So when I study this, I will get to know there are two responses that I observe. Okay? Like I told here, two responses I get. So these two responses will come out as transient response and steady state response. So for every system that operates, we have two responses: steady state response and transient response. So when I have to analyze the circuit or any system with respect to time, it is always necessary for me to consider both the responses. Now the question is, how I can do that? Physically, I showed that this pointer will not rest at final value instantaneously. It will take some oscillations. But how do I represent this in the modular? What model I will propose to understand this? So ultimately, whenever I want to understand anything, mathematics is the tool. Okay? So now I have to mathematize the concept. So here, to understand the steady state and the transient response, and to have that transient and steady state analysis, one mathematical tool which is a boon for us is solution of differential equations. So here what we do is, initially first we will look into how we are getting the solution of differential equations. Then we will apply the already known concepts like KVL and KCL to the circuit, and we will get the circuit in the form of a mathematical model in the form of differential equation. Okay, so any system can be represented with various models. The most fundamental model is a physical model. If it is a physical system, I can have a physical model. Second is the circuit model. So for example, if I have to consider, suppose I have a motor. Okay, I have, say, suppose a motor. Okay, If I see the physical model, the motor will come with, say for example, let us take a DC motor. Okay, a motor will come with poles. I am just drawing for the sake of explaining. Okay, don't judge the correctness of the diagram. These are the poles. I have armature. I am taking example of motor because already you have studied in the fundamental subject. Where you are having the armature, you are having some commutator here, shaft, all those things. So when I show motor in the form of the field, armature, connections, this is the physical model. Physical model. If I have to show the electrical model, the circuit model, then I will show motor in this form. Suppose if it is a DC shunt motor, then I will show this in this form. This is the shunt field winding. This is the armature. The armature is having its internal resistance, Ra. I have a back EMF developed. This is Eb. I have a supply voltage of V volts. Even if I want more refined electrical model, then I will be showing in this form. Back EMF is opposite to the supply. The supply voltage. Field need not to be shown because the voltage across field and the supply is same. Ra. This is Eb and I will show this as Ia. This circuit represents the same motor. So this is physical model, this is circuit model. So this is what? Circuit model. Now, if I want to represent this circuit in the form of mathematical equation, okay, so I can simply apply KVL here and I will write this as V equals to Eb plus IRA, or I can write Eb equals to V minus IRA, or I can write Ia equals to V minus Eb divided by Ra. Now all these three equations represent the same motor. So this is known as mathematical model. So any system can be expressed or represented in the form of physical model. Because I am electrical person dealing about electrical concepts of the system, I go for electrical circuit model. In general, if I want to tell to anybody, I use mathematical model. Okay. So what we are doing in this particular concept of transient study is, I want to get the mathematical model of the system which is represented by the electrical circuit in terms of either source, resistor, inductor and capacitor, to that electrical circuit which is the representation of some such physical model or physical system. Okay. When I write down the equations, KVL or KCL equations, current equation or voltage equations for the particular given electrical circuit, then that will give me the mathematical model. And through mathematical equations or mathematical model, I want to study the transients and steady state response of the system. So this is what we are doing in transient and initial conditions. Okay. And to get to those analysis, I need certain mathematical tools. Like if I say, when I analyze the system using a simple KVL KCL equations, I use matrix as my tool, or I used the system of linear equations where I solved simultaneous equations and got the variables values, and those variables were either representing current or voltage. Likewise, I can use the matrix in the form of Cramer's rule I solved. Again, it is a system of linear equations. Both are linear algebra. Now, that is not sufficient for me. Those mathematical tools which already I used in the linear algebra are not sufficient for me to know the transient analysis or the transient conditions those are existing in the system. For that, I need some other tool, and those tools are differential equations. Those tools are differential equations. So when I say differential equations, two things come to my mind. It can be a homogeneous differential equation, or it can be a non-homogeneous differential equations. Okay. So what homogeneous differential equation mean here in electrical circuit? What non-homogeneous differential equation mean here in electrical circuit? We shall be discussing in detail, and we will be also getting to know what are the solutions, how to find the solution for the differential equation in the particular topic. Okay, with that we start. First we'll see the solution of differential equations, then we'll move ahead for application of these concepts in the circuits by studying what is the nature of R, L and C for a particular type of source given. These all things we will be looking into in detail in forthcoming lectures. Okay? So for today, we will call for the day, and thank you for your patient listening.